I have a question for you. What's the longest time a computer program can run before it stops? A year? A decade? A century? A millennia? Or even the age of the universe? If you don't know the answer, you're not alone. This question has baffled and mesmerized mathematicians for over 60 years. Why? It has surprising connections to some of math's oldest and most famous unsolved problems. It offers a window into where the fundamental logic of math starts to crumble, and could even reveal the edge of what's humanly knowable. And just last year, after 30 years of no progress, a major breakthrough was made. But what makes this discovery truly remarkable isn't just the result, it's the weird way that it happened. It wasn't solved the way most maths problems are solved, by a team of highly skilled researchers at a university. It was solved by an unlikely group of math enthusiasts, mostly without formal academic education, who all met online through a website announcing something called the Busy Beaver Challenge. By the end of this video, you'll know exactly what that means, as well as the surprising story behind this breakthrough and exactly what it was they discovered. It all started with one mathematician and a game he invented. When most people were asking, what problems can a computer solve? A mathematician named Tibor Rado asked, what problems can't a computer solve? How far could an algorithm, a step-by-step, mindless set of instructions, really get us? Were all problems computable? Or were some too complicated for a computer to handle? What are the limits of computation? At the time, the idea of what a computer could solve was well understood, thanks to Alan Turing. He thought up these simple, theoretical devices called Turing machines that capture exactly what it means to compute something. Turing theorized that these simple kind of computers could perform any possible computation. They're the blueprint upon which all our modern digital computers are based, even the computer you're watching this video on. Rado did end up finding a problem that a computer can't solve, and to understand it, we need to know how Turing machines work. A Turing machine is made up of an infinitely long tape divided up into cells. A symbol, like a 0 or a 1, is in each cell. A head reads the symbol, and depending on what it is, can erase it, write a new symbol, move to the left, or move to the right. Every Turing machine has a unique set of rules which tells it what to do. For example, rule 1 might say, if you read a 0, write a 1 in the current cell, move one cell to the right, and go to rule 2. There's also a special rule which tells the machine when to stop running. A Turing machine can have any fixed number of rules. Some have 3 rules, some have 10 rules, some have 100 rules. Usually, the more rules a Turing machine has, the more complicated computations it can do. If you want to know more about how Turing machines work, I've made a whole video about them which I've linked in the description. But here's the important bit you need to know. Starting from rule 1, a Turing machine will either eventually halt or it will run forever. So Turing machines come in 2 types, halting and non-halting. Rado sorted Turing machines into groups according to how many rules they have. He grouped all the 1-rule machines together, all the 2-rule machines together, all the 3-rule machines together, and so on. In each group, some machines will meander along forever, some will halt pretty quickly, and some will take much longer to halt. One will be the last to halt. This was the machine Rado was interested in, the longest running of all the halting machines. Rado named them busy beavers because of how they forage along the tape. The number of steps the busy beaver takes before halting is called its busy beaver number, or BBN for short. For example, for a 1-rule Turing machine, if you want to make sure it halts, you can really only have the rule that no matter what it reads, it halts. So the busy beaver number of a 1-rule Turing machine is just 1, as it only takes 1 step before halting. Getting BB2 is a bit more complicated as there are 6,561 2-rule machines, but it's been shown that busy beaver number 2 runs for 6 steps before it halts. Now here's the cool part. Rado found that finding busy beavers and their busy beaver numbers is uncomputable. There's no general algorithm or formula a computer can perform to find them. The only way to find a busy beaver is to manually examine each machine one by one and see how long they run. He'd found what he was looking for. Rado turned his search for busy beavers into a game. To play, you have to do two things: discard all the non-halting machines and search the remaining machines for the one that runs the longest. Little did he know that this game would have roots in some of math's biggest open problems and turn into a decades-long hunt that would haunt generations of mathematicians. But what do busy beavers have to do with these famous problems? To understand, let's take a look at one of them. The Goldbach Conjecture says that every even integer greater than 2 is the sum of two primes. For example, 4 is the sum of 2 and 2, a prime. 28 is the sum of 17 and 11, both primes. Do this for any even number, and it'll work. This seemingly simple conjecture has defied proof for almost 300 years, yet so far we know that it's true for all even numbers up to 4 times 10 to the power of 18. But checking individual cases isn't good enough for mathematicians. They need hard, logical proof that it's true for all even integers. This is where a busy beaver might come in handy. Suppose you wrote a computer program that checks every even integer starting from 4, one by one, and halts only if it finds a number that cannot be written as the sum of two primes. Such a program has been shown to be computable by a Turing machine with 27 rules. But here's the cool part. If we knew the value of BB27, we could solve the Goldbach conjecture. If our program does halt, then it must halt in BB27 steps or less. If it halts within this number, the program has found an even integer that can't be written as the sum of two primes. This would prove Goldbach's conjecture wrong. But if the machine continues running past BB27 steps, then we'd know it will never halt, as all the halting machines halt before BB27 steps. Goldbach's conjecture would be proven true. So the solution to the Goldbach conjecture can be reduced to finding the 27-rule busy beaver. There are other similar Turing machines for other unsolved problems in math, like the Riemann hypothesis. In fact, any mathematical statement that can be written in a computer language can be proven in this way. It's amazing to think that doing something in a finite number of steps can tell us something about an infinite amount of numbers. So what are we waiting for? Why don't we figure out BB27 and then solve the Goldbach conjecture, and all other unsolved problems in math for that matter? We've seen the 1 and 2 rule busy beavers, but the 3 rule? Well, there are over 5 million 3-rule Turing machines and over 7 billion 4-rule machines. Remember that the only way to find a busy beaver is by examining each machine individually. It's like finding a needle in a giant digital haystack, where the haystacks increase more than exponentially in size as the number of rules gets bigger. But surely we could make our lives easier by getting rid of all the non-halting machines and then just looking through what's left. The non-halting machines are definitely not the busy beaver, as by definition the busy beaver halts. But Turing has a nasty surprise for us. He proved that there is no reliable, repeatable way to tell if a Turing machine will ever halt. If a machine has run for 100 years, it may halt in 100 years and 1 day, and there's no way that we can tell except to just wait and find out. This result is called the halting problem, and I've made a video all about it, which I've linked in the description. It's actually a really cool result, even if it is a pain. So it turns out that both steps of Rado's game are extremely difficult. 1, because of the halting problem, and 2, because there are so many machines to search through. But have we at least found the third busy beaver? Before we get into it, there's a great article on Quanta magazine by Ben Brabaker that details the story of the busy beaver progression really well. I got a lot of the information for this next part of the video from there, so I definitely recommend checking it out if you want to learn more. Okay, here we go. In the mid-1960s, a persistent math grad student at Oregon State University, whose mascot is, coincidentally, Benny the Beaver, gave it a go. His name was Alan Brady, and he realized that he could sort through all 5 million of the 3-state Turing machines if he ignored large chunks of them, such as those that halted immediately. He also recognized that many non-halting machines were easy to spot because they began looping, performing the same instructions over and over. Brady coded up this technique of discarding the obvious non-busy beavers into a computer program. But the average computer at the time couldn't handle that kind of heavy computation. Brady had to drive 90 miles to a town called Beaverton, I'm not joking, to access a state-of-the-art computer at the Oregon Regional Primate Center. But oh no, he was too late. Rado and his grad student Shen Lin had beaten him to the punch. They'd found the 3rd busy beaver. It halted in 21 steps. But Brady didn't lose hope. He immediately moved on to finding the 4th busy beaver. But there was a problem. 4-rule Turing machines can do much more complicated computations than 3-rule ones. This means it was much harder to spot the non-halting machines because many of them don't get stuck in infinite loops, which Brady's program was good at recognizing. But nevertheless, 2 years later, he'd found a 4-rule Turing machine that halted in 107 steps. It would take him several more years of painstaking work to prove that this machine was indeed the 4th busy beaver. Which brings us to April 2024, the Busy Beaver Challenge, and a maverick group of math enthusiasts. Despite there being nearly 17 trillion 5-rule Turing machines, they managed to do what no one else could. They found the 5th busy beaver and BB5. Okay, we actually need to jump back for a sec. Around 20 years after Brady found the 4th busy beaver, the University of Dortmund held a competition to find the 5th busy beaver. Over 100 contenders showed up, but by the end of the competition, no one had conclusively found BB5. However, one contestant had found a machine that halted in 100,000 steps. The contest was reported in Scientific American, which popularized the game to a new generation of mathematicians, and this number soon blew up to over 2 million steps, pushing the potential BB5 up even higher. But everybody was shocked when grad students Heiner Markson and Jürgen Buntrock discovered a 5-state machine that halted in 47,176,870 steps. Was this the 5th busy beaver? They had no idea that it would take over 30 years to answer this question. Progress was slow going for decades, but things really took off in 2021. A grad student named Tristan Sterren tried out Brady's original method, with a twist. Like Brady, Sterren wrote a code that weeded out machines that obviously weren't the 5th busy beaver. He collected all the remaining machines and dumped them into a database for examination. By December 2021, the database was complete and held over 88 million machines. 88 million possible busy beavers. If he could show that each of these machines either halted before 47 million steps or never halted, then he would know that this 47 million step machine really was busy beaver number 5. But how was he going to sift through this mountain of 88 million machines? Sterren knew he needed help, so he founded the Busy Beaver Challenge, an online community anyone could join. Around 20 people from all around the world started working on the problem, and most of them didn't have any formal mathematical training. They just did math as a hobby or for fun. Together they began chipping away at the 88 million machines, keeping the others updated on their progress through Discord. But there was a big problem. Some machines were nearly impossible to classify. One in particular developed an especially scary reputation. They called it Skelet Number 1. What was tricky about it was that it would sometimes act completely predictable and sometimes completely wild. There was really no telling what it would do next. But after months of bashing their heads against a wall, 2 contributors finally managed to crack it. Sean Ligocki and Pavel Kropitz showed that Skelet Number 1 did finally settle into an infinitely repeating loop. But after more than a trillion steps, At long last, they'd managed to classify it as a non-halting machine and remove it from the list of potential busy beavers. But there was a doubt growing in everyone's mind. Could they trust the code they wrote? Even if they did find BB5, any small error in the code of the program would make their result worthless. They needed to prove that their code was free of errors. But how can you prove that thousands of lines of code have no errors? This is where a new and unlikely player joined in with a secret weapon, a proof checker. Proof checkers are programs that don't run if they come across a logical error, so mistakes are virtually impossible. A good proof checker program could confirm beyond a doubt that the team's proof was free of faulty logic. An ambitious university dropout and self-taught programmer, May, stepped in. May translated Skeleton No. 1's proof into a proof-checking language called Coq, verifying Ligoki's and Kropit's result that Skeleton No. 1 never halts. Little by little, the mountain began to dwindle, with proofs of non-busy beaverness trickling in from other participants. But many proofs still hadn't been translated into Coq to make sure they were legit and error-free. Then, on May 10th, 2024, a mysterious participant named MXDYS made an announcement. The Coq proof of BB5 is finished. They'd compiled the group's work into a single 40,000-line Coq proof. It was the final step in the Busy Beaver 5 mission. An unlikely team of individuals from all over the world who had come together over their love of math had finally proven that this 47 million step Turing machine was the 5th Busy Beaver. It was a momentous feat, but sadly, not everyone got to celebrate. Alan Brady, the finder of the 4th Busy Beaver, died just a few weeks before the proof was finished. He was 90 years old. Though he didn't live to see this milestone, his legacy will always be intertwined with the story of the Busy Beaver. So what's next for the Busy Beaver saga? Some of the team are already busy hunting for the 6th Busy Beaver, but it isn't looking good. They've shown that BB6 is at least 10 to the power of 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 10 steps. We wouldn't even be able to run a machine for this long before the predicted heat death of the universe. So it's quite possible that BB5 is the last Busy Beaver number we'll ever know. But some of the Busy Beaver Challenge team have moved on from Busy Beavers. May has become obsessed with the European International Rail Network and is aspiring to be a train driver. Will humanity ever find BB6? There are nearly 60 quadrillion 6-rule Turing machines. With numbers this big, the odds are stacked against us. But if there's one thing this story has shown, it's that when people want to get to the bottom of something, they'll find a way, no matter how impossible it may seem. The drive to understand, solve, and explore the unknown is what makes us human. It makes me wonder, what made us like this? Where did this insatiable curiosity come from? What were the moments in our evolution that made us the smartest species on Earth? The answer to these questions are actually fascinating, and my friends over at Real Science have made an entire series that explores these questions, plus many more, like the origins of language and the breakthroughs that made us uniquely human. It's called Becoming Human, and I highly recommend it. It's one of my favorite things on Nebula right now, a platform that's quickly becoming the go-to space for the best educational content on the internet. Nebula is built and run by creators, with the mission to be the best place for us to make work that we couldn't make anywhere else. I've always wanted to take my videos to the next level, and Nebula is enabling that for our entire list of creators. Better stories, better production value, taking creators to the next level is what Nebula is all about. And there are countless examples of what we're capable of, and it's only getting better as time goes on. It's completely ad-free, and most creators post their YouTube videos there a week early. To check out Becoming Human, as well as hundreds of other top-notch, thoughtful videos, completely ad-free, sign up with my link to get 40% off. That's just $3 a month or $36 for the entire year. Seriously, for the price of a latte, you're getting access to some of the most interesting and creative content out there. Go to nebula.tv/upandatom or click the link in the description. You'll be supporting this channel as well as the entire educational community. Thanks, and I'll see you next time. Bye!